And so today we're going to continue on 10.2, okay, which is looking at some more properties about circles. Today we're going to focus a lot on arcs, okay, and chords. All right, so first way we're going to look at is what's called a central angle. Okay, if you draw an angle and its vertex is right in the middle of the circle, it's called a central angle. Kind of like if I did something like this. If I draw an angle, put the vertex right in the middle. What I just drew in red, that's a central angle. And let's label some points here. Let's call this A, B, and we'll call the center of the circle P. If that angle that I just drew is less than 180 degrees, okay, which it is here, okay, then A and B, this point and this point, and the points that are on the circle and in the interior of the angle. That's these points right here. What I just circled, or what I just highlighted in green, those points are on the circle and they are inside that red angle. They form what's called an arc. Okay, specifically because the angle is less than 180, this is called a minor arc. Okay, what I just drew in green. So basically a minor arc is where if you take your angle and you draw it, the two spots where the angle hits the edges of the circle, between those two spots, that's an arc. Okay, but it's only called a minor arc if the angle is less than 180. In this picture, there's two arcs. There's a minor arc, and then there's a bigger one on the outside. Anybody have a guess what that one's called? It's not a minor arc. Yeah?
Major arc.
Yeah, we have a major arc. So we'll get to that right now. Right, so now if you look at points A and B, and look at all the points that are in the exterior of that angle. In other words, all the points that are not between the two rays of that angle on the perimeter. That's a major arc. Okay, I think I got another picture. Like that. Okay, so angle APB, there's your angle. Between A and B, going the short way, that's a minor arc. Between A and B, the long way, that's a major arc. And there's a relationship between the size of this arc and the size of this angle, which we're going to learn about in a second. Okay, any questions on what a minor arc or a major arc is? When we talk about arcs, we're only talking about parts of a circle. If you had an ellipse and you wanted to look at part of an ellipse, we don't consider that an arc. Okay, we're only going to be studying circles. Okay, if the endpoints of one of your arcs were basically the endpoints of a diameter, then you'd have a semicircle. Okay, let me sketch that. Okay, here's the center of your circle. Okay, draw the diameter. If I were to make an arc, okay, from here to here, going like that, because the endpoints of my arc are right on the endpoints of a diameter, I just covered half the circle. Okay? That's a semicircle. Anyone think they know how big that arc would be in red? Yeah, it is. It's 180 degrees. Yep. All right, so how do you name an arc? Okay, basically you just name it with the endpoints. So if you had, again, I think a picture would help here. Oops. Let's draw an angle. It's A, P, B. If you wanted to describe this arc right here, that's how you do it. You just say arc AB. Doesn't matter if you say arc BA, that's the same thing. Okay, so to name a minor arc, you only need 2 letters. If you want to name a major arc, that's a little different. We've got to use 3 letters. Okay, but to name a minor arc on a circle, just name the 2 letters that are the end point of the arc and put this little curved symbol above them. Okay, we've seen symbols above these letters before. What's another symbol we've seen above those letters that means something else? So this is arc AB. We could also have what other kinds of things?
Line, segment.
Yeah, line AB, segment AB, ray AB. Right? So now you got one more, arc AB. Okay, if you want to name a major arc or a semicircle, you're going to still use the endpoints, but you need one more point that's on the arc. Okay, like point C. Now, if I wanted to name the major arc, one that goes like this, I could call it arc ACB. Right, and now there's no confusion whether I mean the small arc or the big arc, because I used A, C, B. You just trace along that path, you get the major arc. Okay, any question on that? Okay, so on the test, if I ask you to name an arc, 2 letters for a minor arc, 3 for a major. Okay. All right, so now we're going to get into how do you measure an arc? Okay, what is the size of it? Well, the size of it is related to the central angle. In fact, it's the same. The measure of a minor arc is exactly the same size as the central angle. So if you had an angle in a circle that was 45 degrees, the arc corresponding to that would also be 45 degrees. Right, so the measure of an arc is the same as its central angle. Okay, here's an example. Angle GHF is 60 degrees. Arc GF is also 60 degrees. How do you think you could get the measure of the major arc here? Arc GEF. If you know the minor arc is 60, what could you do with that to get the major arc?
You subtract 60 from 360 degrees.
Yeah, if you subtract 60 from 360, you'd get the major arc, arc GEF, or you could say FEG, same thing, and it would be 300. Okay, so the measure of a major arc is the difference between 360 and the minor arc, just like Luke said, 360 minus 60 in this case. The reason we use 360 is because a full circle, that's 360 degrees. So you're basically taking away the minor part and you're left with the major part. Okay, any question on that? All right. Let's try a couple problems. Okay, so I want to find the measure of each arc I've listed below. Bless you. In circle R. Everybody have what's on the left so I can make the right a little bigger? Yep. All right. Anyone think they could tell me the measure of arc MN? Okay. Well, first of all, can you just tell me what kind of arc MN is? Is it a major arc or a minor arc? Yeah. It's a minor arc. So the definition, if you know the size of the central angle, that's the size of your arc. So in this case, arc MN is how much? 80. Yep. 80 degrees. All right. Now I want to find arc MPN. Okay. Without even a picture, because I use 3 letters to label it, most likely it's what kind of arc? It should be a major arc. We don't use 3 letters for a minor arc, generally. Okay. MPN. How would you find that arc? Yeah?
60 minus 80.
Yeah. Take the minor arc, subtract it from 360. That'll give you the major arc. So it's 360 minus 80. James, what's 360 take away 80? 280. Good. Don't forget your degree symbol. Everything, all our measurements are going to be in degrees. There are other ways to measure angles, but we don't study them in this class. Okay, and what's the last one they want? Arc PMN. Okay, PMN. Well, a hint for that is look at segment PN. What kind of segment is that? Yep. I don't think we have a mid-segment defined for a circle. We have mid-segments for triangles. Okay, we talked about that term with triangles. But what's the term you'd use to describe PN here? Yep? Diameter. Okay, that's a diameter. You could also say it's a chord, but you could be even more specific and say it's a chord that goes through the center. Okay, it's a diameter. Well, if you've got a diameter and you want the arc that has its endpoints on the diameter, we said earlier how big the arc would be. So how big is the arc with endpoints right on the diameter?
180.
It's 180. Yep. 180. Okay, when your arc is 180, you do have to use the 3 letters. Because if I went back up to the picture and I said, find an arc here that's 180, well, there's 2. Do you want PMN, which is the bottom part, or would you want, and I'd need to put a point up here, do you want the top part? Okay. So there is a difference. Anytime you name an arc that's 180 or larger, use the 3 letters. Okay, questions on that? All right, so next word is adjacent. Okay, so 2 arcs in the same circle are adjacent if they intersect at exactly 1 point. What's if somebody had trouble understanding the word adjacent? Jacob, what's a simpler way of explaining what the word adjacent means? Like if I said I'm adjacent to the table right now, what does that mean? Or I'm adjacent to the board. Just in everyday life, like what's the word? Like if I said, oh, it's adjacent to the building across the street. Like what does adjacent mean?
The intersection of
just like forgetting like geometry speak, just like everyday kind of life if you use the word adjacent. Like if I said my book is adjacent to this pile of papers. Adjacent means what? It means they are, does it mean they're far away from each other? Nope. Means what? They're right next to each other, right? So if you have two arcs that are next to each other on the circle, that means they're adjacent. Okay, draw in this arc. Okay, and I'll use a different color just so we can see it. Draw in this arc. Notice though I'm going to have the two arcs share one endpoint. The arcs in green and the arcs in blue are adjacent. Okay, that's a picture of it. Any question on that? Adjacent arcs? How do you think you'd find the length of the arc in blue and green? Say from this endpoint to that endpoint. How would you find the length of that whole arc if you knew the length of the blue one and the green one separate? Yeah.
You could add them together.
Yeah, you'd add them together. Okay, this is the arc addition postulate. We've had segment addition postulate, angle addition postulate. This is exactly the same idea, except it's for arcs. Okay. The measure of an arc formed by two arcs that are adjacent is the sum of each arc. Okay, here's another picture. The measure of arc ABC is equal to the measure of, let's see. No, let me fix that a little bit. Let's get two of the letters off. Now I think we're good. Okay. The measure of arc ABC is arc AB plus arc BC. Okay, that's called the arc addition postulate. Okay. Any question on that? Okay. Pretty simple idea, but it's an idea that might come up in a more complex problem. Okay, kind of like this one. Right, so I've got a circle, and I've got four different arcs in it. Well, four different individual arcs, like GH, HE, EF, FG. Okay, and I'll make it a little bigger so we can see the angles. Okay, angle GRH is 40, HRE is 80, ERF is 110, and FRG we don't know, but we could probably figure it out if we need to, keeping in mind what all the angles should add up to. Okay. And the first thing I want to do is find arc GE. Okay, so we're going to use that postulate we just learned. How could you find the length of arc GE? Yeah.
Add arcs J or GH and GE.
Yeah. It's going to be arc GH and which one?
HE.
HE. And both of those arcs we know because we have their central angles. Arc GH is 40. HE is 80. It's a tenor. What's the measure of arc GE?
120.
Yep, 120. Good. Okay, arc GEF. Well, how could you find arc GEF using part of what we just did? You could go back and kind of do it from scratch, or you could somehow use part of what we just had. What two arcs could you add together to get arc GEF? And again, let's try to recycle some of the stuff we already got. Yep?
Could add together each
Arc, which one?
or each no G
Yep, GE. Take the one you just had.
and EF.
Plus which one?
EF.
EF. That'll give you GEF. EF. Now, you could have also done GH plus HE plus EF, but you've already done GH plus HE. Okay, so let's just reuse it. Okay, what's the measure of our GE? Oh, Morgan? So what do you think the measure of arc GE is? We found that in the last step. 120. Arc GE is 120. All right. Okay. How about EF? How big is that arc? Sarah? Yep, 110. Good. Okay, so add them up, get 330. Okay, and the last arc I want to find is GF. Well, again, try to reuse some of what you already have. You just found this. Now I'm asking for this other part here, arc GF. How do we get that? Yep.
Why did you say 330?
It doesn't add up to 330?
No,
Oh, 230, thank you. Yes, 230. 230. All right, so now, still same question. How would you get GF? Oh, Olivia?
Take 230 and subtract 360.
So take 230 minus 360? All right, that's going to give us a negative arc.
360.
Yeah, 360 minus 230. All right, so 360 minus the 230. Since I have trouble with arithmetic, can somebody tell me what that is?
One.
It's like 900, right?
One.
What is that?
130.
120?
130.
130. Okay. All right. So congruent arcs. Okay. One thing we have to understand about congruent arcs is they don't have to be in the same circle. They can be in different circles that are congruent. Okay. So two arcs of the same circle or of congruent circles are congruent if they have the same measure. But the key is the circles have to be congruent or the same circle. All right. So I'm going to give you some pictures, and all I want to know is, are the arcs congruent? Yes or no? Okay, how about in A? Is arc AB and arc GC, are they congruent? Are we dealing with arcs in the same circle in this case? Yep, there's only one circle in that picture. So do each of those arcs have the same measure?
Yes.
Then yes. Arcs in the same circle, arcs with the same measure, yes. Those arcs are congruent. Okay, this one. Are we dealing with the same circle? No. Are we dealing with congruent circles?
Yes.
Yes. I've marked the radius congruent in each circle. That's all you need to know to prove a circle congruent. Same radius. Okay, so we've met the first one. Congruent circles. Do they have the same measure?
Yes.
Yes. Then those are congruent. Last one. Do we have the same circle here? No. Do we have congruent circles? No. These are not congruent arcs. One other question. Do the arcs have the same measure?
Yes.
Yes. Both of these arcs are 65-degree arcs. They have the same central angle, but the circles are not congruent, and they're not the same circle. So you've got to have both of those, either the same circle or congruent, and the same measure. This just has the same measure. Okay, question on that?
All right.
All right, what does it mean if you have a midpoint? Well, in a segment, it basically means it's a point that if you measured the distance from that to the end point and that to the other end point, it would comes out the same. Well, it's the same idea here. So let me make a sketch of that. Okay, so here's arc X. We'll make that Z. We'll make that Y. Okay, here's my arc. If arc XY and arc YZ are congruent, then Y is the midpoint. Okay? So if arc XY and arc YZ are congruent, Y is called the midpoint. All right, so the next three things we're going to look at are all theorems about chords. They're long. So my advice would be, I'm going to put down the page, and that might be the best thing to look at. Okay, it's all on page 605. If you want to copy them down. I think the best thing is, I want to just try to explain them, do an example with them so you understand them. And then at least you can get them. I just copied what was in the book. All right, so theorem 10.4. Okay, this theorem says that if you have the same circle or congruent circles, two minor arcs are congruent if and only if their corresponding chords are congruent. Okay, remember, if and only if means you can read it forwards and backwards. So in the same circle or congruent circles, two minor arcs are congruent if their corresponding chords are congruent. Or you could say, if their corresponding chords are congruent, then the minor arcs are congruent. Okay, so here's a picture of that. All right, so I have arc AB. Okay, that's one arc. Then I have arc BC. I'm saying those two arcs will be congruent as long as AB and BC are congruent. Okay. AB is the chord that corresponds to arc AB. BC is the chord that corresponds to arc BC. And if I had another segment in there, segment AC would be the segment that corresponds to arc AC. I didn't draw in segment AC. We don't need it. Okay, so if two chords are the same measure, then the arcs are going to be the same measure. As long as you're dealing with the same circle or congruent circles. If you have two circles that are different sizes, then that doesn't work. Okay, 10.5. 10.5 says, in a circle, if you draw in a diameter, and it happens to be perpendicular to a chord, then you just cut the chord in half. Okay, so if you draw in a diameter, and the diameter is perpendicular to the chord, it will cut the chord and its arc in half. Okay, let me show you a picture of that. Okay, I have a diameter, okay, in that circle. I also drew in a chord, DF. Where DF and the diameter cross, it's perpendicular. If that happens, then this chord was just cut into two equal parts. And this arc, DG and GF, would also be two equal arcs. Now, a chord doesn't always have to be perpendicular to the diameter. You might say, well, isn't the chord always perpendicular to the diameter? No. If I drew it like this, there's no way that that chord and the diameter make a 90-degree angle now. So in that case, the two parts of the chord are definitely not equal. One's a lot longer than the other. Okay, any question on that? Yep.
So what you're saying is if that diameter is there, it cuts it in half, but if you dimension it a different way, like have it going up, it won't cut it in half.
Well, so what I'm saying is if the diameter and chord are perpendicular, then it cuts it in half. As long as you have a 90, it cuts it in half. In theorem 10.6 is just taking this theorem and looking at it as the converse. So rather than saying, okay, we've got a chord and a diameter that are perpendicular, which means it cuts the chord in half, let's start with cutting the chord in half. Okay, so if you have one chord in a circle, and you draw in another chord, and it bisects that chord into two equal pieces, then you just drew a diameter. There's no way you can draw, if you've got a circle, and you put in a chord, there's absolutely no way that I can draw another chord through that diameter, and if it's going to cut this in half, it has to be the diameter. It has to be. So let's say your midpoint is right there. Guarantee you, if you draw a segment through that point, it's going to have to be the diameter. Assuming you draw it perpendicular. I mean, you could draw it like this. This is different. That's not perpendicular, though. Draw a segment straight through there. Make that a 90. You just drew the diameter of the circle. Okay, actually, I already had a picture. Okay, so any question on that? So draw a chord, draw another chord perpendicular that bisects it. Guarantee you that other chord is going to be the diameter of the circle. Okay, we're going to use this idea in a second to figure out something. Let's say you had a really big circle, and you wanted to figure out perfectly accurately where the center was. Using this theorem, you can do that. I mean, let's say you had a huge circle, like 1,000 feet across. You could find the exact center using this theorem. All right, let's try an example here. Okay, so we've got two arcs. Okay, one in red, one in blue. What do you notice about the two chords corresponding to the red arc and the blue arc? They're congruent. If the chords are congruent, then the arcs are what? Then the arcs are congruent. So 2x is going to equal x plus 40. Now from here, we just use algebra and solve that. Subtract x, and you're done. That's it. Oh, I'm sorry. Actually, we have x. They want the measure of arc AD. So if x is 40, how big is arc AD? 2 times 40. 80. Be careful when you solve it if they want to know x or they want you to plug it back in and find something. How about arc DC? 80, they're congruent, remember? So they're the same. All right, let's see how we could use theorem 10.6, okay, to find the center of a circle. Okay, this is something I just want you to watch how you do it. Draw two chords in the circle. The key is do not make the chords parallel. If you draw parallel chords, this won't work. Okay, so there's two chords. Mark the midpoint of each chord. Okay, so maybe, I don't know, about like that. Maybe about like that. Now, if I draw in a segment that's perpendicular to that chord and goes right through the midpoint, then that segment would have to be a what? It would have to be a diameter, right? So I've got that one. Now do it one more time. You're going to get another diameter. Okay, maybe about like that. Where those diameters cross, what must that be? It has to be. Okay, if you have two diameters in a circle and they cross, well, that has to be the center of the circle. Okay, so that's how you can find the center of a circle. Draw two chords, draw in a perpendicular bisector to each chord. Where they cross, that's the center. The only thing you can't do is draw your chords parallel. Then you'd have two diameters right on top of each other. They wouldn't cross. Yep.
Couldn't you just have two diameters, essentially? Just find the center.
Yes, but if you're doing a construction, I don't know how to construct the diameter. I mean, you can't just go like this and say, oh, that kind of looks like a diameter. It might be off a little bit. You know what I mean? So this gives you a way that you're constructing the center. I didn't measure anything here. We learned early on how to construct lines perpendicular to each other, so we could use a compass to do this. There's no guesswork at all. All right, and our last theorem. This is on page 606. All right, so again, if you have the same circle or two circles that are congruent, two chords will be congruent if they are equidistant from the center. So if you draw two chords in a circle and you measure how far each one of them is from the center, if they're the same distance from the center, they're congruent chords. They're the same length. And when you measure the distance from something to a point, how do you measure it? Like if I wanted to know my distance to the back wall, would I measure it over towards the corner? Is that how far I am from the back wall?
Or you do
Straight, perpendicular. If I want to know the shortest distance to the back wall, I go from me straight to the back wall, perpendicular. Okay, so what we're saying here is AB is a chord, CD is a chord. If this distance and that distance come out the same, the distance measuring straight, right to the center, then those chords are the same length. Okay? But you don't measure how far a chord is from the center by measuring it off at a side or at an angle. You measure it straight to the center. Okay, I think this is kind of one of the harder theorems to understand. All right, so this will be our last one. All right, in this diagram, AB is 8, DE is 8. Okay. AB and DE are both what kind of shape? What term would you use to describe them in that circle? They're chords, and they're congruent. If two chords are congruent, what do you know about them? equidistant from where?
Center.
The center. So whatever GC is, so is CF. So we have to find CF, but if we can find GC, it's the same thing. That's true by theorem 10.7. Okay, let's make that a little bigger. Look at segment CG. What's point C in this circle? It's the center. You've drawn a line from the center perpendicular to that chord. What do you know has to happen if you do that? Anytime you draw a segment that's perpendicular to a chord and it goes through the center, it's a diameter. CG is part of the diameter. What did we say earlier? If you have a diameter and a chord that are perpendicular, that cuts it, the chord, in half. So now we know DG and GE are the same.
So we know AF and FB is the same too.
How long is DE? 8. So how long is DG? 4. Now look at this triangle in that circle. Let me draw it down here. This is 4. This is 5. How can you get the third side of a triangle? Use the Pythagorean Theorem. X squared plus 4 squared equals 5 squared. I'm going to find GC. Okay. I'm finding this. That's not what they want, but that's okay. If I find GC, it's congruent to what they want. So once I find GC, I'm good. So x squared plus 4 squared equals 5 squared. Okay, how do we get 16 on the other side? Subtract. So how big is x? 3. And remember, x is a length. In this case, you don't use the negative 3, because length can't be negative. Okay, so now you've got GC, but that's really the same as CF, and we're done. Okay, so these kind of problems with circles and chords and arcs, they can get kind of tricky. I think this is kind of tricky. But if you just look at it one step at a time, you can figure it out. Okay, so that's a good one to put on your notes. You could almost think of this part on the bottom when I told you of a footbridge earlier that you're walking across, and you wanted to know how long that horizontal line was. That problem is kind of along the lines of this. So if you want to look at one like that before the test tomorrow, we can. Okay, so the homework is on 607. Okay, it's 3 to 10 all, 13 to 33 just odd, and 33 to 37 odd. And try the open response. Okay, that's about a pyramid. I think it's about a pyramid. Okay, we'll go over that before our test tomorrow.